So in this video, I'm gonna talk about Kubernetes. So let's understand what Kubernetes is, and I will also talk about some of the jargons that you might come across when learning Kubernetes. So consider this video as a beginner's Kubernetes understanding. So I'm gonna walk you through one of my blog posts that I wrote some time back, named Kubernetes Demystified. So by reading this blog post, you should get a very high level understanding of Kubernetes and what it is created for. So before we dive into understanding Kubernetes concepts and jargons related to Kubernetes, let's understand how the application landscape has changed over the years. So years ago, and even still today, some of the applications are built as what we today call as monolithic applications. So what we mean by monolithic application is that an application that has everything bundled together, its dependencies and its configurations and whatnot, those kind of things are all configured in one application, and different components, modules of that application is also bundled with that, so that that application, when it comes to deployment, has to have all of those dependencies and modules and configuration files and plugins and whatnot. All those needs to be in one form, even if the application is handling different sections, different business problems and so forth. All might be running as one single process. So these kind of applications is what we call as monolithic applications. While these applications are great, and there are many examples of such applications today, but today's applications and businesses actually demand high level scalability and agility when it comes to application development and so forth. This monolithic application architecture doesn't fit well. So one reason is when it comes to scalability, as I mentioned, how do you scale this application to cater for additional traffic, you may call that way, right? So in that sense, this application needs to be either vertically scaled, which means you need to allocate more resources for this application in terms of CPU, memory and so forth, or else you need to think about horizontally scaling. Horizontally scaling means you add maybe another node of this particular application in the same server that you are running this application, or in another server, which is great. But thing is, as your requirements for scaling goes high, you need to keep on adding more and more nodes, even though at times your scalability requirement is only on one part of the domain problem that is addressed by this application, but at the same time you are kind of scaling the entire thing. So think about scaling an entire box that has a lot of components. Even though you need other components to be scaled or not, you are just scaling to address one part of it. So it also poses a lot of other challenges when it comes to hardware requirements, because you are scaling a big thing now, right? And the other fact is, the application might not have been designed for such scalability as well. So those are the problems when it comes to monolithic applications. So understanding this problem, today's application landscape, especially when it comes to distributed applications, have come I have come to a kind of a conclusion saying applications need to be divided in a way that the components or the modules of that application can be deployed independently and developed independently as well. This is what actually led to this concept called microservices architecture. So let me just once again circle back to monolithic application. So a monolithic application might be running in a physical machine or a virtual machine, and so let's consider this as the monolithic application that has different components within it, and you can't separate these things. It will always be together, because that's how the monolithic applications are designed. So when it comes to scaling, you will have to scale this entire thing. You can't scale these individual parts separately. Let's say the scalability requirement is only on this A component, but not on the B and C component, because to meet the requirements for A, you are still scaling B and C as well, and in multiple servers. So this poses those problems that I mentioned. To address that, the microservices architecture was born, and microservices architecture separates or segregates these services or these domain components of your application will be separated as minuscule services. Don't get the word minuscule wrong. It doesn't have to be minuscule in the way that it's really small. It doesn't have to be. If it's kind of addressing one specific business problem, that's fine. You can consider that as a microservice. So you can separate it out, and then communication between each of these microservices can be in the form of standard protocols such as REST APIs, GraphQLs, or some other inter-process communication methodology such as with a queuing mechanism such as AMQP protocol and so forth. So as far as that interface can be met, these domain services or domain problem services can be developed independently and can be deployed independently. So this is what one of the advantages of microservices architecture is. So now think about scaling the component A. So you have one component A, and now you have to scale it 4 times or 4 folds. So you have done it this way. And C doesn't have a scalability component, or it doesn't have a scalability requirement, so it just remains as is. And B has scalability requirements, and that goes independently. It doesn't have 4 components like the A, and it just has 3 components and so forth. So, and you can have these scalability requirement addressed with the microservices architecture. In fact, the C component, depending on what you have done, actually may not be scalable because of technology issues that or technology limitations that you may have. So that can even pose requirements or it can hinder the scalability need of a monolithic application. So you have this need, and you have this simple component C which is not scalable, let's say, when it was implemented. Then even though you wanted to scale it up, you can't scale. So this is one of the advantages of going with the microservices architecture. Now, the microservices architecture is great, but thing is, as you have like hundreds or even thousands of microservices in your platform, things are going to be really tough when it comes to deployment. Can you deploy thousands of microservices and make sure that the dependent microservices and other components are all in order to make sure that application doesn't have any problems? So microservices on one hand bring a lot of advantages, but on the other hand it also brings challenges. So this is where Kubernetes type of container orchestration platform comes into play. So now the containers are important in this. It's going to play a very vital role in the microservices architecture. It is playing today. Thing is, now when it comes to these microservices, you need to make sure that all the dependencies of this microservice is only visible to this microservice. Let's say this particular microservice and this particular microservice has the same dependency but 2 different versions of that dependency. So having both of these microservices deployed on a virtual machine or a physical server is going to pose a lot of challenges in making sure that that particular microservice is actually loading the correct version of the dependency. So that's not possible. So that kind of an isolation can be brought in by introducing the container technology such as Docker. So one good thing about Docker type of container technology is because it's based on Linux, and underneath this possibility comes in containers because of Linux's namespace concept. So that in a particular namespace of Linux, you can isolate or just virtualize the hardware's view. For example, the CPU, the network interface, and you name it, right? Even physical layers of hard disk and so forth, and process ID and so forth. So same process ID can be assigned to two different microservices running on two different Linux namespaces. So a similar concept applies for dependencies as well. Anything that's loaded in one Linux space is not visible in the other Linux namespace and so forth. So this is the concept that Docker actually exploited in the Linux world to make it into the mainstream. So container platforms like Docker or Rocket, Rocket is another container platform, they achieve this isolation, application isolation, quite well. So that application isolation is now there, but when it comes to the scalability and making sure that you have multiple instances of these microservices running in your specification and so forth, when you have hundreds of microservices and running in containers, you need a container orchestration or container management platform. So Kubernetes is one of those container orchestration platform. There are many others as well. For example, Mesos is another container orchestration platform. Docker Swarm is another container orchestration platform. But by far, Kubernetes has won the war in container orchestration. So it only makes sense for us to focus on Kubernetes today. Things can change in future, but it's very much evident that Kubernetes has sort of won the war in this space. So let's only focus on Kubernetes in that. Have these microservices bundled as containers, and according to what we want to achieve here, and in the Kubernetes world as well, there needs to be a way of telling how many of certain unit, might be the containers, let's say, you want to have in this cluster. So in the Kubernetes world, this cluster is called the Kubernetes cluster. It's a fleet of nodes where these containers or anything that it considers as a unit will be deployed in, right? In Kubernetes world, why I've been telling whatever else, maybe containers or whatever else, is because in Kubernetes world, the unit is actually not the container. So what they call as a pod, the unit is a pod. A pod can have just one container, in which case the pod hosts just one container, or a pod can have multiple containers. So for example, I have, let's say, A, B, and C microservices bundled inside containers, and you can define in Kubernetes A and B containers should always be together, and then you call it a one pod, and then the container C should be isolated on its own in another pod. And then you can specify in Kubernetes world saying, I need to have two pods of this particular pod that hosts both A and B containers. I just need to have one pod of where this C is hosted and so forth, right? So, and in Kubernetes cluster, let's say you have three servers, or wherever, physical machines or virtual machines or whatever that is. Let's call it Kubernetes worker nodes. So in reality, we can call it Kubernetes worker nodes. How these two pods of these containers get deployed, and where this C pod, let's say the container, the pod that is having container C getting deployed, is something Kubernetes will decide. It might use one pod of this here, another pod here, and host the pod that has the container C together with one of those pods. Or in another configuration, or even within the runtime, at some point, it could change the deployment topology in this way. So both of these pods could be running in one server, and this pod could be running in the third server, and in the second server there is nothing. So this is what actually called Kubernetes scheduling. Kubernetes as a scheduler, we'll talk about its components in a while, will decide where things will be running, and it's very dynamic, and even the user doesn't need to know. Like if you are the application developer and the person who is deploying your application into Kubernetes cluster, you will actually not know in advance where these pods will be scheduled to run. There are ways to figure it out where it is running once it is scheduled and running, but before it gets run, you have no way of determining where it will be running. And okay, so that's about pods and so forth. And in real world Kubernetes, to interact with Kubernetes, you will need to have some tools installed in your platform. One of the key command line tools that you will be coming across is this kubectl, or some people call kubectl, or some people call kubectl. And for your interest, you might come across people calling Kubernetes as I'm pronouncing here, or some people call it Kubernetes, right? So whichever way you prefer to call it, I'm pretty sure that you will recognize the other person is referring to what you think is Kubernetes, right? So that's don't consider that as a major issue. So kubectl command is the utility that you will be using in the command line to interact with the Kubernetes cluster, and in fact what we call as Kubernetes master. So in a sense, this is what actually the Kubernetes components distribution would look like. So actual containers would be running in a fleet of nodes, as what we call as Kubernetes worker nodes. So you will have 2, 3, or 10 of those running. And in a Kubernetes cluster, there will always be a node, what we call as the Kubernetes master. So kubectl is a tool that you will be having in your machine, which is like consider that as a client machine, right? So with this kubectl, you will specify certain containers, and you define the deployment topology and everything in some form, and you give a command to kubectl to instruct to this Kubernetes master, saying, this is my configuration. I want in this form of pods, containers within pods being distributed in my Kubernetes cluster. So within the Kubernetes master, there is a component called the Kubernetes API server. So Kubernetes API server is a component that will interact with the kubectl, and it will also interact with other components in the Kubernetes worker node. Specifically, there is this component called kubelet and kubeproxy will interact with the API server. In fact, API server will also communicate with some of the internal components here as well, especially the scheduler and the controller manager. So basically, the API server is how it's a you can consider that as a central piece of component that helps communicating between other components, right? And so basically the scheduler is what actually specifies where the pods should be running in the Kubernetes worker nodes, and this information will be available in the scheduler. And when the kubelet is another component which will always in a periodic intervals, maybe it will check with the API server, saying, is there any new pods that's been assigned to some of the nodes here, or some of my nodes here, and if so, it will do further processing, let's say. So that information is decided in the scheduler, and the kubelet will ask from the API server to get that information across. Controller manager is more of another component that will make sure that always a certain number of pods are running. As I said in previously, we mentioned that we have specified 2 pods of these should be running. Let's say for some reason one of this pod get killed due to an issue in your components or the container, or even in this case, let's say this server disappears because of a hardware failure, then Kubernetes' job is to make sure that always 2 pods are running at all times. So it will make sure that this gets scheduled to this server or this server, and making sure that the required deployment is always kept in a consistent state, right? So this etcd, so I have these descriptions written down here. So API server is the component which kubectl and other internal Kubernetes master and worker node components communicate with. etcd is a persistent distributed data store for Kubernetes configuration. So when you have configurations given here, and there will be other implementation intricacies involved, so we're not going to go to there, and if you're interested, you need to dive into a more advanced material, maybe a Kubernetes book to learn about all those things. So in the etcd, you can consider that as a persistence store to save some of the Kubernetes related configuration. And the scheduler, it schedules the pods for deployment in relevant worker nodes, as I mentioned. The scheduler will make sure that happens. The cluster controller handles node failures and replications of the pod, just as what I mentioned previously. So it just makes sure, okay, it will know certain pods are running, it will monitor, it will do what we call as the controlling. So all of this together, this Kubernetes master, all these components together is sometimes called the control plane, because that's where every controlling mechanism happens. Okay, and then in the Kubernetes worker nodes, you have these three components: the kubelet, kubeproxy, and the container engine. As I said, these microservices and pods will host containers, right? So that means Kubernetes will have to work with a container platform such as Docker, right? But Kubernetes in fact supports other container platforms like Rocket as well, but let's consider Docker as the container platform here for ease of reference and discussion, right? So kubelet is the component in the worker node that communicates with the API server to see if any pods have been assigned to it, and if so, uses the underlying container engine. So it will check with the API server here, and if there is a pod assigned to it, it will make sure, okay, inform the container engine saying, okay, there is a new pod assigned to you, go do your job. So this container engine then might go fetch it from a remote Docker repository, or if the Docker file is already there, it will just do the local work, whatever. That sort of work will happen there. So kubelet will let know the container engine, this is what you need to do, and so forth. The kubeproxy is a Kubernetes network proxy that load balance the network traffic to the pods. Now, as I mentioned, these let's say these pods can get scheduled into different nodes in the Kubernetes cluster. So it's kind of a moving environment, right? So how do you how does Kubernetes make sure that a consistent interface or consistent IP address or whatnot is provided to other containers or other pods or other external entities to use those services? So Kubernetes makes sure that it provides that IP address, and this kubeproxy makes sure within the pod or within that particular node that load balancing takes place accordingly. So okay, so this is all when it comes to the fundamentals of Kubernetes, but now you need to do the real work, right? So the real work for you to do something, you need to have a Kubernetes cluster set up. So setting up a real world Kubernetes cluster with multiple nodes and whatnot is going to be a complex task, but it's not that hard. There are materials available in the internet, and there are books available so that you can follow. And if possible, I will try to cover one of those in a future video as well. But at least you should be able to test something on your local machine as well. So for that, there are multiple ways of doing that. So there is a tool called Minikube. So Minikube actually is a container, it's a platform that allows you to run a Kubernetes cluster locally. So it will be a single node cluster. Obviously within your machine, it will spin up a virtual machine or a hypervisor, and will you use that as the Kubernetes worker node, and possibly that as the master node as well. And when you install Kubernetes, you will also kubectl command, you can interact with Minikube just as you would interact with a real world Kubernetes cluster, and you can make sure you do certain testing there, create a pod with a container and deploy it, and test out some of the commands you can do. But in real world, the Kubernetes cluster could be running in let's say in a data center with multiple nodes, and someone has set up the Kubernetes worker nodes and the Kubernetes master manually, or actually where the Kubernetes shines is in the cloud. So these mega cloud vendors like Amazon AWS and Google and Microsoft has services for Kubernetes. So for example, Amazon has Amazon's Elastic Kubernetes Service, EKS platform, and Google's Kubernetes Engine, GKE platform, and Microsoft's Azure Kubernetes Services platform, AK, is there. So if you want to explore, you can also make use of those platforms in the real world as well. So that's all I was thinking to cover for today as a beginner's uh, you know description of Kubernetes, and to understand some of these jargons like kubelet, kube proxy, cluster controller, schedule etcd, and so forth. And if you come across now, you know what that means. And so I'll meet you in another video with some of to see how to use this kubectl command to interact with a Kubernetes cluster in real world. But before I wind up, so just as I mentioned Minikube, so if you have installed this Rancher desktop, for example, it also brings in Docker as well as Docker Compose and Kubernetes as well to your local machine, so that you can do some testing there. And so we'll explore this in another video. So I recommend that you just go through Rancher desktop and see what functionalities it provides, so that you are ready to play around with Kubernetes. We'll meet you in another video. Take care and goodbye.